Hello, everyone. So, in this discussion, we are going to look at the GATE 2022 problems from the aerodynamics side. There are a few of them, and let's try to look into how to solve them. So, the first question, consider a two-dimensional potential flow over a cylinder. If the free stream speed is u infinity, the maximum speed on the cylinder surface is. So what they're telling us here is, so you have a two-dimensional flow, um, and it's over a cylinder, uh, and it's a potential flow. So basically, going back to the potential flow topics. So there's a flow over this, and the free stream velocity is u infinity. Now, what they want us to find is the maximum speed on the cylinder surface. So, since it is a potential flow, the speed on the surface of the cylinder will not be zero. It'll have some value. And they want us to find first tell us the first we need to find at which location that is going to happen. Because, it could happen at any given point, on the cylinder surface. And secondly, the other part of the question is what is the value of that maximum velocity? So, and you can consider that it's a non-lifting flow over cylinder because they haven't talked really anything about the circulation, the value of circulation, etc. So, going to the non-lifting flow over cylinder, we know that the velocity on the surface of the cylinder, let's say the cylinder has a radius r, the r directional velocity is 0 on the surface of cylinder, which is understandable because you cannot have perpendicular velocities. And the tangential velocity is given by minus 2 u infinity sine theta. That's basically the velocity. So now let's say, at any given point, the net resultant velocity would be nothing but the sum of the square root of sum of squares of them. So that is ur square plus u theta square. So that will basically give us the magnitude of velocity we are talking about. So that will be nothing but 2 u infinity sine theta itself, because ur is 0 and you're only left with u theta. So there are two ways. So here to find, so this expression gives you the velocity at any given theta value. So that is, you take the cylinder. So the measurement of theta happens in this way, anti-clockwise. So this is 0, this is 90, this is 180, this is 270, etc. So now you need to, find at which location you can expect the maximum velocity to be. So you can easily find that the maximum velocity will occur at a point where sine theta is the maximum. So sine theta should be maximum. So we know that sine theta maximum value is 1 max value, and that basically occurs one at 90 degrees and one at 270 degrees, or 3 pi by 2. So since as long as we're concerned only about the direction of magnitude of velocity, let's take theta equal to 90. So velocity is equal to 2 u infinity sine 90. So that will be nothing but 2 u infinity. So the maximum value of the velocity that can occur on surface of the cylinder is nothing but 2 u infinity. That's option C. All right. Now, next question is based upon the lifting line theory and the three-dimensional flow field, to be precise. So what they're telling us is that there's a circulation distribution over a finite wing given by this particular equation. So, so let's try to visualize this. So there's a wing, and there's a circulation distribution over the wing. So let me mark the center. So this is y equal to 0, and let's say my coordinate system goes this way. This is y direction, and this is x direction, let's say. So along the span of the wing is my y direction. So what they're telling us here is, and each section is of length, let's say b by 2, b being the entire span. So a circulation distribution is given such that it is gamma naught into 1 minus 2y by b when y is between 0 to b by 2. So that is between the right half, on the right half where my y is between 0 to y by 2, my circulation is given by the equation gamma naught into 1 minus 2y by b. So let me write that down. So on the right side, my equation is gamma naught into 1 minus 2y by b. So basically, let's say if my y equal to 0, my circulation value is gamma naught. So if I were to plot this, it looks something like this, right? So this is my y-axis. So at y equal to 0, this will be gamma naught. Say gamma naught. It will be gamma naught, and at the tip of my wing, that is when my y equal to b by 2, if I substitute that over here, so this becomes 0. So my circulation goes from gamma naught into gamma naught to 0 on the right hand side of the wing. All right. And what happens on the left hand side of the wing? So the equation on the left hand side of the wing is given by gamma naught into 1 plus 2y by b for minus b by 2 to 0. That is the left hand side. So on the left hand side, the equation being gamma naught into 1 plus 2y by b. Let's try to plot how it looks. So at y equal to 0, it's obviously gamma naught. There cannot be discontinuity here. And then y equal to b by 2, you're getting 2y naught. So which means that if I would need to redraw this figure just to fit it in space. So this is the right hand side, 0 to positive b by 2. So this is, it varies linearly. And from minus b by 2 to 0, you are basically is gamma naught over here. And then it increases to 2 gamma naught. So this is basically how my circulation is distributed on my wing. Now what they're asking us is, if the wingspan is 10 meters, so meaning that each half is 5 meters, the maximum circulation gamma naught is 20 meters square per second. Density of air is 1.2 kg per meter cube. The free stream speed is 180 meters per second. Find the lift over this wing in newtons. So the idea here is to find the total lift. So now we know that, with the help of gamma, you'll be able to find what is the lift at any given section. So let's say I take a very, very small strip of this wing, and let the small strip be of length dy, right? Let it be of size dy. So the lift per unit length over this small region is defined according to Kutta-Joukowski theorem as, let's say, since it is a small region, let's say infinitesimally small region, so let me call it dl, that is lift per unit length. Lift per unit length, it's lift per unit length, which means that what is the lift over that particular airfoil section. So let's say so the lift per unit length is nothing but rho infinity, v infinity, and gamma at that location, whichever is the location where my strip is. Now that is for a given airfoil section. Now if I want to find what is the total lift over this small strip dy, so I would basically need to multiply this lift with dy. So the infinitesimally small amount of lift that is contained in that small strip is given by rho infinity, u infinity, gamma of y into dy. So keep in mind, guys, here, so this is lift point length, that is the lift on a given airfoil section. So and then so this uh, lift on a airfoil section and just multiplying it with the length of that airfoil, which is nothing but dy, and hence you get the infinitesimal small value of lift. So now to find the total lift over my entire wing, I would basically have to integrate this guy, minus b by 2 to plus b by 2 rho infinity u infinity into gamma of y into dy. So rho infinity, u infinity are constants, and so I'm left with rho infinity, u infinity equal to gamma of y times dy, and the limits being minus b by 2 plus b by 2. And now we know that gamma is not a continuous function, it's just a function which is variable throughout the length. So from minus b by 2 to 0, it has one value of one functional form, and from 0 to b by 2, it has another functional form. So let me split the integral accordingly. So my lift, total lift, I need not use this apostrophe. So apostrophe is usually used for infinitesimal small, for airfoil, let's say, lift per unit length. So the total lift, let's say in this case, is nothing but rho infinity u infinity into integral minus b by 2 to 0 gamma of y dy plus integral 0 to b by 2 gamma of y dy. All right. And now what I'm going to do here is just substitute the equation. So lift is nothing but rho infinity u infinity, and from minus b by 2 to plus b by 2, the equation is given by gamma naught into 1 plus 2 y by p whole thing into dy. And for the other half, 0 to b by 2, it is gamma naught into 1 minus 2y by b into dy. All right. So out of this, I can take the gamma naught common from both these and then take it. It's a constant, right? So let me rewrite it as L into rho infinity u infinity gamma naught into integral minus b by 2 to 0 1 plus 2y by b dy plus integral 0 to b by 2 1 minus 2y by b dy. All right. So now all we need to do is just integrate it. So the total lift is nothing but rho infinity u infinity gamma naught. So the first integral term will be nothing but u plus y square by b under the limits minus b by 2 to 0 plus the second integral is nothing but y minus y square by b into 0 to b by 2. All right. So now applying these limits, and you can substitute the values as well. So my rho infinity is 1.2, b infinity is 80, gamma naught is 20, and then applying the value of b is 5. So applying that as well. So what I'll be left with is something like this: 5 minus 2.5 plus 5 minus 2.5. So 2.5, 2.5, that'll take up a 5. So 1.2 into 80 into 20 is your lift in Newtons. So that's nothing but 9,600 Newtons. That is the total lift over this entire wing. So it's very simple. Just need to understand the concept. If you had If you guys are clear about how the lift is derived from Prandtl's lifting line theory, then this would be a piece of cake. It's a very, very simple problem. So 9600 newtons. Go to next question. In a conversion area duct, the converging area duct area and velocity at section P are 1 meter square and 15 meters per second respectively. The temperature of the fluid is 300 Kelvin. So what they're saying is at this, if you look at this converging duct, so flow is going to accelerate over this converging duct, right? So at location P, the pressure is the area is 1 meter square, velocity is 50 meters per second, and the temperature is 300 Kelvin. Air flows through the nozzle and can be assumed to be inviscid and isothermal. So the flow is inviscid, viscosity 0, and the temperature is constant. And the characteristic gas constant is 287, ratio of specific heat is 1.4, so on, so on and so forth. To ensure that airflow remains incompressible, that is, Mach number is less than or equal to 0.3 in the duct, the minimum area required at section Q is. So what is the minimum area to which I can reduce my section Q so that my Mach number is less than 0.3? So you guys can easily understand that the flow is going to accelerate, right? Based upon how small this area is. The smaller it gets, higher the acceleration. Now we want to find what is the least area that I can go to at location Q. What is the least value of it, such that my Mach number is still either less than or equal to 0.3. So the least area is achieved when my Mach number will be 0.3. Least area that is required by the question is achieved when my Mach number is 0.3, right? So I do not want to cross 0.3. So Mach number 0.3 is the maximum velocity that I can achieve. I should be achieving in this case, and my area will be that much narrow accordingly. So my target is to achieve Mach number at location Q to be 0.3, and I can find what is the velocity at what velocity is required at location 3 by just multiplying it with root of gamma RT. And since it is an isothermal flow, so look that both P and Q, the temperature is going to be 300 Kelvin. All right, so my velocity at location Q would be nothing but gamma, that is 1.4 1.4 into 287 into 300. All right. So with that, and so this is the velocity, and now we can apply our mass conservation principle over here, or a continuity equation over here. So my and it's an incompressible flow. We are flying. The flow velocity is less than 0.3 Mach. So it's an incompressible regime. So my volumetric flow rate would be the same, or density would be same at both location P and Q. So rho AP VP should be equal to rho AQ VQ. And rho will get cancelled because density is the same. We are the incompressible regime. So AP, the area is 1 meter square, velocity is 15, and the area over at location Q is something to be found, and the velocity at location Q is nothing but 0.3 into root of 1.4 into 287 into 300. All right, and doing the calculation, you will find that the least area that I can go to is 0.144 meter square. So this is the least area that I can have at location Q. So rounding off to two decimal places, it will be 0.14. All right. Now the last question here. Consider a thin symmetrical airfoil at angle of attack 2 degrees in a uniform flow at 50 meters per second. So you have a very thin symmetrical airfoil. Let me draw a thin symmetrical airfoil. So which takes us back to the concepts of thin airfoil theory. So the angle of attack is basically 2 degrees and the velocity is 5 meters per second. The pitching moment coefficient about the leading edge is. So from thin airfoil theory concepts, we know that at the leading edge of a symmetric airfoil, the pitching moment coefficient is given by, at the leading edge, is given by minus CL by 4, where CL is the coefficient of lift. So in this case, it will be nothing but 2 pi into alpha by 4. It's a symmetric airfoil, so there's no 0 degree angle of attack. So this is minus 2 pi. Alpha is nothing but, you need to, so it's given in degrees, you need to convert to radians because my 2 pi is in terms of radians. This is 2 into pi by 180 divided by 4. So 2 to 4 gets cancelled, and this is minus pi square by 180. And my coefficient of moment at the leading edge is nothing but minus 0.055. Non-dimensional value. So around to 3 decimal place would be 0.055. It's a very simple problem, direct application of the formula, nothing very tricky over here. So these are the questions from the aerodynamic side of things. So very simple problem with good clear concepts and easily recollectible formulas. These are quite a simpler set of problems.